Hey, what's up, guys? This is Cheng here. So today, let's take a look at today's daily challenge problem number 329, longest increasing path in the matrix. So you're given like m times n integers matrix, and you need to return the length of the longest increasing path in the matrix. And so the path only happens uh, in 4 directions, right? And you may not move diagonally or outside of the boundaries. That's why in the example 1 here, we have, so the longest increasing path is 4, where we start from 1 and we go this way and we end at 9. And similarly in example 2 here, right, we have another path which is has the length of 4 as well, right? And here are some constraints, right? So the constraint is like 200, right? And then the numbers is within the integer numbers. I mean, obviously, this one is the it's a DFS, right? So it's going to be a recursive call, right? Because so the way we're calculating the longest path is, so the naive approach is that we start at each of the cell here, and for each of the cell, we'll try to calculate the longest path, right, by using the DFS. Basically, so we'll go to the direction, right? We'll go to the direction where from this current one, we go to the direction of go 4 directions, and we only go to the directions where the next number is greater than the current one, right? And then while we're doing that, we're also gonna pass the current level or the current path length, right? And in the end, we're also gonna maintain the longest path, right? But as you guys can see, that's the time complexity for that. It's gonna be so let's say we have an m row and it's m times n, right? So it's going to be a m times n cells. For each of the cell, we're going to do a DFS. So the DFS, the worst case scenario. So for each of the cell, we're gonna iterate the entire board. So it's going to be another m times n, right? This is going to be the time complexity. This one obviously I mean it will work, right? But can we improve that? So basically, at each of the cell, so at each of the cell, what I'm saying is that, if I define like a DP problem, because, so the way we're using DP is that, so with the bigger problem, we can split it into a smaller sub problems, So what does that mean in terms of this problem, this question? So let's say we have DPI here, right? So we have DPI and J here. So DPI and J means that, the longest path, actually the longest path ending with I and J. Okay, so let's say for example we have 9 here. So the dp00 equals to what? Equals to dp this is 0 0 1, right? Sorry, this is 1 0. dp10 plus 1, right? Actually this is equals to the max of the dp10 plus 1, and then also the dp of 0 1 plus 1, right? Because oh, this one is not valid actually. So we're only gonna consider, since we're saying that this dpij means that the maximum length ending at I and j. So we can only have a sub problems when the neighbor is smaller than the current one. That's why the sub problem of the dpi and j dp00 is a dp10 plus 1, and then again this dp1 can be further split, right, into another sub problems, which is going to be the max of its neighbor, right? Now it's 6 9 and 2, but 9 and 6 is they're both greater than 6. So the only valid subproblem for the dp10 is the dp20 plus 1, right? And so on and so forth. At the end, we have 1 here, where 1 does not have any neighbor who is smaller than itself. That's why we'll basically the recursion call will stop at 1. So what's the benefit of doing this? Basically, every time next time when we see another 6, right? Let's say, for example, if this one is 7, if this one is 7, so next time when we are, when we calculate 9 at the first time, we have the result of dp9, dp6, dp2, and dp1. So for example, if we have 7 here, when we try to calculate the longest path of dp7, right, we'll look for 6, right? But at this time, 6 has already been calculated, right? That's why we can simply just use the result from the previous calculation, and so that we don't have to recalculate 6, because otherwise, if you don't memorize the result, like what we are doing here in dp here, when we calculate 9, we'll calculate 6 and then 2 and 1. So when we calculate 7, we're also gonna calculate 6, right? And then again we have 2 and 1. Basically, we're like repeating the duplicate work here. That's the purpose of dp. Basically, we store the previously calculated result in the place, so that we don't have to do it over and over. And yeah, I think that's it, right? So basically, we just use the dp I and j this to store the longest path ending with the I, ending at this location, and then and then on top of this, we're gonna try each of the cell, right? And cool. Let's get on to the coding then. And so let's see, we have dp here, right? Define dp I and j. So in Python, we have this kind of shortcut, right, where you don't have to write the additional code to memorize, to create like a dictionary, and then to memorize this the result for I and j. So this LRU cache none in Python will do it for you. So assuming we have the dp functions, right, and then and this one actually is the longest path ending at I and j, right? And then we're gonna have like directions, right? So as always, 4 directions, and then 0, 0, 1, 0, -1, right? Then we have m equals to the length of matrix, right? N is the matrix dot 0. So we have the answer. We start from 1 because the smallest answer we have is 1, right? So for I in range of m, basically, like I said, I try each of the coordinates, right? For j in range of n, right? So answer equals the max of answer dot dp of I and j, right? Because I and j give us the max length ending at I and j, and we just need to try all of them, right? And we return the answer in the end. And now comes on this dp here, again. So the answer is also 1, right? Start from 1. For d in directions, so new I equals to I plus d0, right? And then new j equals to j plus d1. Okay, so we need to check the boundaries first. So if the new I is within the m, and the new j is within the n, right? And right, the last condition is that the neighbor has to be smaller than the current one, right? So that's we can so that can be a valid subproblem, right? So the matrix new I and new j needs to be smaller than the current one, right? Only then we can just do a recursive call on that, right? It's going to be 1 plus dp new I and new j, right? And in the end, we return the answer. So as you guys can see, so we starting from 9, we'll keep going to the sub problems until we have reached 1. So when the dp I and j is pointing to here, you know, with answer is 1, and but for the for loop here, you know, we'll never go into this sub problems again, because we cannot find any neighbor who is smaller than the current one. That's why when we reach the 1 here, it will simply skip this for loop here, and then it will simply return 1 in the end. Okay. And we don't have to memorize the visited set for each of the DP here. You know, usually when we try to do a DFS or BFS, we're gonna have like a different set state structure, so that we will not end into a infinite loop, but here we don't, because we have this kind of check here. So which means that, you know, we start from 9, and then when we reach at 6, of course we're gonna try to check all the neighbors out of 6, but for 9 it will never be smaller than so basically the parent will never be smaller than current one. That's why we'll never go back to the node to the cell we have visited before. And yeah, so let's run the code here. Accept it, right? Cool. So it works, right? I mean, so the time complexity is, of course, we have m times n, right? And for each of the cell here, we do a dp here, but you know, since for each of the cell in the dp will only calculating that cell once. So that's why, you know, we have m times n plus m times n, right? And still it's, so the time complexity will be a m times n time complexity, because whenever we see like a cell we have calculated before, this dp, this Python thing, this cache thing will just simply return. Right. Yeah, I think that's it, right, for this problem. And yeah, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.